Today the topic is thermochemistry, and we will clarify your concept about thermochemistry. I will have a narrative for explaining all these topics I have written, like heat of hydration or internal energy or state function or His law or first law of thermodynamics. I have knitted them together in a narrative, and I'll explain them with the help of MCQs. Is the definition of the thermochemistry. I have provided in MCQs. You have to mark your answer. So I'll do this with the whole chapter. With the help of MCQs, I'll clarify your concepts. The first MCQs was mentioned in the paper of 2005, ETA 2005. The study of the heat changes accompanying chemical reaction is. So what are they saying? They are saying that you have claimed that chemistry is the science that deals with the study of changes in matter. As carbon combines with oxygen, the matter changes from one shape to another shape. So there is another thing associated with that change. That is the heat. So have you given a special branch this task? Have you assigned a special branch this task to study this heat of this change? Your answer to this question must be yes. And if I ask you what is the name of that branch that you have given the task of studying the heat associated with changes in matter, you must tell me that I call that branch of chemistry thermochemistry. Therm from heat and chemistry, as we know, chemistry. So this is the answer to our first question. The study of thermochemistry, we must know few preliminaries, like what are the important things I must know before I delve deep into thermochemistry topics. I must know about the system. What is system? So now I have like zoomed this word from the whole board surrounding it. So this is under my observation now, just this word. So as a scientist, anything under your any part of the universe, anything under your observation is a system for you. So anything under scientific observation is the system. And what is surrounding anything else other than our system? So this system is a system for me now because it is under my observation. So if it was under my scientific observation, I would have called it system scientifically. So system is anything which is under our scientific observation. I must repeat it. System is anything which is under my or our scientific observation. So now we'll go to the next MCQs, and I must ask about system. So if you were able to know the system, the definition of the system, so you must answer the question that was mentioned in the paper of 2018. That was asking that students were decomposing calcium carbonate placed in a china dish by heating using burner in a laboratory. The system, like in this experiment is. So you must know the system. They are decomposing what? Calcium carbonate. So that is under their scientific observation. So you must know that anything under our scientific observation is our system. Neither is the china dish, nor the laboratory, nor the burner. But what is our system? Our system is calcium carbonate, which is under our scientific observation. So now we till this point we know about the basics of thermochemistry, that what is its definition and what is the system. Now we will go further and define. Before going deep into this topic, we must know a few things. Two basic concepts of thermochemistry is state function and path functions. So what are they? State functions are those physical properties of the system that are independent of the path followed by the system. So it does not depend upon the path on which the system has reached that state. They just depend upon their initial and final values. Okay, if their initial and final values are the same, you will get the same amount of difference irrespective of the path followed. So to prove this with the help of graph, I must draw a pressure volume graph. Okay, I here on this side I have pressure, on this side I have volume. Suppose I started from a point of pressure and volume. Suppose this is P1 V1. Okay, and I reached some point P2 V2 through a path like this. Okay, now again I'm trying to reach from pressure P1 V1, like from this point P1 V1 to that point P2 V2 with another path. Okay, this is path 1 followed by my system, and this is path 2 followed by my system. Here in I'm going to prove that as long as my initial and final destinies are the same, I will have the same values for state functions. So here we can distinguish between state functions, what are state functions and what are path functions. So I found out that delta P in case 1 was equal to delta P in case 2. So what I found was delta P as I followed path 1 was equal to delta P as I followed path 2. So this proves, pressure is proving that it is a state function. It is independent of the path followed by the system. What I also saw that delta V in case 1 was equal to delta V in case 2. I mean, change in volume in the first scenario was equal to change in volume in the second, though the path followed by the system in both cases were different. But here we can also go for another thing, that is work done by the system. So work done, how can we calculate the work done? In this case, we can calculate the work done. Work done is equal to the area under the curve. So in this case, the area under the curve is the blue area. But in case 1, we have the area under the curve, that is shaded area black plus blue. So in both cases, we have W1 not equal to W2. This means that work is proving itself to be a path function because it is depending upon the path followed by the system. So I can write work over here. It is proving itself to be a path function. Alongside work, we have another path function, that is heat. Heat also depends upon the path followed by the system. But here, pressure, volume, internal energy, enthalpy, entropy of the system, they are independent of the path. They just depend upon the initial and final state of the system. So they are state functions. So hope I have cleared my point. I can also give another analogy. Yesterday this came into my mind that suppose you are filling up a jug with water. So independent of the path, you can fill it from down here or up here. It does not depend upon how you filled it, but at the end what matters is how much you have filled it. Like delta V would be equal to V final minus V initial. So independent if you have filled it with drops or you have filled it by flooding it, it does not depend upon it. You have filled it from a tap or you have filled it from a pipe. What does depend it? Its final state and its initial state. So this is a state function. I cannot simplify it further. The concept we just built, now we can solve this problem. The most repeated MCQs of this chapter, uh, that is, which one of the following is not a state function? So we have to find out a path function from out of these four options. And we already know that we discussed that work and heat were path functions. They depended upon path followed by the system. So if work and heat is mentioned in one or any of these options, we must offer that, and that is yes, it has been mentioned over here. work is in path function. So now here to elaborate further on this concept, I must say, can we convert a path function to a state function? You must answer this question. Can we convert a path function into a state function? You must answer it. And I will answer that yes, we can convert a path function into a state function. How? If we restrict the path of the path function. How we do that? As we know that heat is a path function. Path function. I must write it like PF. Okay, PF means path function. So can I convert heat into a state function? Yes, I can do that by restricting it. Like we say QP, heat evolved or absorbed by the system at constant pressure, is a state function. And what we call that state function, we call it enthalpy. Okay, and what is enthalpy? Enthalpy is the total heat content of the system. Okay, so how can we mathematically write it? It is enthalpy equals what? The internal energy plus pressure volume work of the system at constant pressure. So can we find the absolute value of enthalpy? No, we cannot find the absolute value of enthalpy. We can find the change in enthalpy, that is equal to change in internal energy plus pressure volume work at constant pressure. At constant pressure. Okay, now we know the mathematical form of the enthalpy. Enthalpy is a very useful term for a chemist. Through this, he can know the spontaneity of reactions. He knows that those reaction in which heat is absorbed to them, he calls endothermic endothermic reactions. So to those reactions in which heat is absorbed, those reactions are called endothermic. And what are those reactions? Those reactions are like the reaction in which bonds are broken, like atomization. Okay, so because in atomization we break the bonds. Like suppose I have iodine bond. If I provide energy to it, it is an endothermic process. I provide energy and break the bond apart, and I form atoms of iodine. So I go from iodine molecule to iodine atom, and this process is endothermic because I'm ripping apart bonds. And exothermic reaction, those reaction in which heat is evolved, the heat is given out to the surrounding. So the heat evolved from the system. Uh, like I'm supposing in this case the heat of hydration or heat of neutralization or heat of electron affinity or lattice energy, because it is evolved in these processes. I will say hydration, enthalpy of hydration heat or enthalpy of hydration. For negative and positive values of the reaction, you must remember that we chemists have a sympathy for our system. So anything that is adding into the system, we are taking it as positive. So anything that is taken out of the system, we take it as negative. So you must remember this trick. Now I will go to the MCQs part and give you MCQs on this formula, and then on these things, what is endothermic and exothermic reaction, and also this formula. So I will now go to the MCQs part. These are the previous paper's questions on the concepts of enthalpy we just discussed. So the enthalpy change is measured at, as we said, at constant pressure. Okay, the change in enthalpy at constant pressure is equal to, I told you to remember the mathematical form of it. It is the sum of the change in internal energy plus pressure volume work at constant pressure. So then, which one of the following is not endothermic process? Not endothermic. As we discussed, atomization of I2 is endothermic because there is breaking of bond. Condensation of water. So for condensation of water, you need to remove heat from the system. So the condensation of vapors is an exothermic process because it is evolved from the system. So we must mark it as not endothermic process. So on the concept, we just discussed about enthalpy of the reaction and also endothermic and exothermic reactions. This is the question. Providing heat for the following reaction causes it shift to the right. So if we provide heat to this reaction, the reaction goes in forward direction. Means if we provide heat goes in forward direction mean endothermic. Okay. Therefore, the reaction can be described as, so as I said, this is endothermic process. And we can also say that this reaction is endothermic because if you reverse this reaction, this could become exothermic and spontaneous. This is the combustion reaction, the combustion process. If we burn methane in the presence of oxygen, we will get carbon dioxide or water, but excess amount of heat. So this reaction is exothermic in this direction, so obviously it will be endothermic in that direction. So our answer should be endothermic. Yes. And spontaneous, no, it is not spontaneous. It is spontaneous in the backward direction. So this is the answer to the question. So as this is the discussion of enthalpies, we will discuss also the enthalpy of hydration. It is the amount of heat evolved. Heat evolved when 1 mole of gaseous ion, like ions in gaseous form, are dissolved in water, okay, to give us an infinitely dilute solution. Infinitely dilute solution. So we must remember this definition. What happens is when we dissolve some ion, suppose this sodium ion in water, what will happen is oxygen from water will surround, as oxygen bearing negative charge will surround the positive charge ion. So during this process, what happens is the energy is liberated. It gives us energy. Okay, so this is ion dipole interaction. Ion dipole interaction. This ion dipole interaction depends upon the charge on the ion and size of the ion. So it is directly proportional to a charge on the ion and inversely proportional to the size of the ion. Delta H is directly proportional to charge on the ion and inversely proportional to the size of the ion. Greater the charge on the ion, we will have greater amount of energy evolved as enthalpy of hydration. Smaller the charge on the ion, we have lesser amount of energy evolved as enthalpy of hydration. So now we will solve previous paper question on this concept. These two are the previous paper questions. First is saying which of the following has the largest heat of hydration. So as mentioned earlier, heat of hydration directly proportional to delta H of hydration is directly proportional to charge and inversely proportional to size. So we must find the greater charge and smaller size. We must look at the options: barium plus 2, potash plus 1, lithium plus 1, and beryllium plus 2. So the tie is between plus 2's. So as the size of beryllium plus 2 is smaller than barium plus 2, So beryllium plus 2 wins over barium plus 2. Now you have to look at this MCQs. It is saying that calcium plus 2 ions are more hydrated than sodium ions because these are why calcium plus 2 ions are more soluble, more hydrated than sodium ion. So we know that calcium is positively charged, double positively charged. Sodium is monovalent, like it has plus 2 charge. More charge means more energy of hydration. More energy of hydration means more hydrated. So it is divalent and sodium is monovalent. Another thing is, though their sizes are comparable, but still calcium has smaller size than sodium, though the difference is just 2 units, as we know that there is diagonal relation between these two. So they are on diagonal, means they have comparable sizes, but still uh, calcium wins on both fronts. First, it is divalent, divalently positive, and it has smaller size, so it wins over here. So option D is the correct option. Another MCQs that was posed in 2012 paper was about the definition of heat of hydration. So you must know the definition I have written is, okay, so it was posed in 2012 paper. So this means that it is necessary you must give real toward the point that the ions must be in gaseous form, and then there must be one more to form infinitely dilute solution. So these are few points you must remember them because it was mentioned in paper of 2012. Now we must move on to other concepts about enthalpy of the system. There are different enthalpies of the system, like it is not just one enthalpy. But you must remember one thing, and that is enthalpy, standard enthalpy of element at their standard state. So we have arbitrarily given the value of 0 to the enthalpy of the elements in their standard state. So enthalpy of the elements, suppose like sodium. I am taking example of sodium. Sodium solid at 298 Kelvin, I mean room temperature, and 1 atm pressure, its enthalpy is taken as 0. So it must be 0, not sodium liquid. Okay, I must take the enthalpy of the sodium metal at 298 Kelvin, I mean room temperature, and 1 atm pressure. Its enthalpy will be 0. As well as carbon in graphite form, its enthalpy is carbon graphite is 0, not in diamond, not in diamond state. Its enthalpy is not 0 in diamond state. So the most stable state of an element, its enthalpy, its standard enthalpy is taken as 0. So what would be the enthalpy of mercury liquid? It will also be 0. But if I have to take mercury in solid, it will not be 0. Okay, then if I have to take, suppose chlorine in gas form must be 0. Cl2 at 298 Kelvin and 1 atm. Okay, bromine. What do we bromine find it normally in? Bromine molecule like Br2 normally is in liquid state. Okay, iodine I2 normally we find it in solid state. So at room temperature and 1 atm normal pressure, 1 atm pressure, we will have iodine as in solid state, bromine liquid, mercury in liquid state, carbon graphite form. So all of these we must take their enthalpy in standard state as 0. So you must remember that their enthalpies in these states would be 0. So now I must go toward MCQs. and I'll provide you MCQs and you must mark your answers. So as discussed earlier, that the enthalpy of elements, the enthalpy of formation of elements, or the enthalpy of elements in their pure form, in their standard state of 298 Kelvin in 1 atm pressure, their enthalpy is arbitrarily taken as 0. I have discussed that earlier. Now we will look at the question. The enthalpy of the elements at 1 atm pressure and 298 Kelvin is arbitrarily given the value of 0. Now look at another question that was posed in the previous paper. For which one of the following the standard heat of formation is not 0? So these are different elements, okay? Chlorine, sodium, bromine, etc. So we must mark the element that is not in its natural state. The state of 1 atm pressure and 298 Kelvin, like bromine liquid, its enthalpy of formation must be 0. But here bromine is not taken as liquid, it is taken as gas. So its enthalpy of formation must not be 0 because it is not in its natural state. And mercury, normally in liquid state, so it is here given as liquid. So its enthalpy of formation would also be 0. So why not bromine? Because bromine is normally found in liquid state at 298 Kelvin and 1 atm pressure. Till now we discussed different enthalpies. After this we will discuss that enthalpy of the reaction is a state function. It does depend upon the initial and final state, does not depend upon the path of the reaction. But here, after discussing so many enthalpies like enthalpy of hydration or enthalpy of formation or enthalpy for standard enthalpy of elements and etc. And here we will be able to discuss enthalpy of neutralization. As said earlier, now from enthalpies I will go to first law of thermodynamics, and then from thermodynamics I have to prove that enthalpy is a state function, and that has been proved by his law. What does his law say? It is saying that enthalpy is a state function. What does this mean? That enthalpy delta H depends upon the initial and final state of the system. It does not depend upon the path followed. So his law is saying that the summation of enthalpy in a cyclic process is equal to 0. What does this mean? If you start from a certain point and then you come back to that point again, it does not depend upon the path followed by you. As long as you come back to the same point, you will have the same enthalpy. So enthalpy change in a cyclic process is 0. Okay, so he says that when a reaction is happening, suppose A is going to B, it does not depend upon this. If A is straight away or just one step goes to B, or it is going to C, then D, then to Z, and then to B. It does not depend upon the steps. So in both cases, we will have delta H for path 1 or path 2. So delta H of path 1 will be equal to delta H of path 2. So there are lots of application of his law. One is the Born-Haber cycle. What does Born-Haber cycle is used for? It is used for calculation of lattice energy, which what is lattice energy? Now I will define lattice energy and solve any MCQs on that lattice energy. Then we will go to the details of his law and Born-Haber cycle. Now we have reached the point that we can say that energy throughout a chemical process remains conserved. So this is a statement which has become a law now, that energy is remain conserved, and in thermodynamics it is called the first law of thermodynamics, which says that energy is neither created nor destroyed. It just changes forms, like it can be converted from heat into internal energy or it can do work. So the heat given to a system could change its internal energy or do some useful work. So this is the first law of thermodynamics could be written mathematically as, or if I switch the sides, I can say that Q minus W is equal to E, internal energy, or switching one variable to the other side is not making any difference. So the change here, what is this saying? That the change in internal energy could be brought about by the heat provided to the system or work done by the system or on the system. So we can play around with this equation now, but the main point is that energy remains conserved during the whole process of thermodynamics, during the whole thermodynamics process. So after long discussions on enthalpies, now we are able to prove that enthalpy is a state function. And that proof is present in the His law. His law says that the enthalpy of a reaction, if it happens in one step or in multiple steps, will remain the same. So one of the applications of the His law is Born-Haber cycle. And Born-Haber cycle is an indirect calorimetry used for two fast reactions like finding the lattice energy of ionic compounds. So what is lattice energy? We will look at that now. But first of all, we will discuss the formation of an ionic compound step by step. Okay, I will take the example of sodium chloride as an ionic compound. So what happens is in sodium chloride formation, sodium solid combines with chlorine gas to form sodium chloride crystal. Okay, and evolve 411 kilojoule per mole of energy. So this is delta H of formation of sodium chloride. But there are steps involved in the formation of sodium chloride crystal. And I will write them down one by one. And then we will see the proof. Okay, first of all, the sodium. The sodium happens to be in the solid form, so we have to convert it into gaseous form. So sublimation of sodium is the first step of this process, or we consider it. So what happens is sodium solid is converted into sodium gas, and it requires 109 kilojoule per mole of energy. So delta H of sublimation is 109 kilojoule per mole. Then I have to convert this sodium into sodium ion. For the ionization, I need ionization energy. So sodium from the gaseous form is converted into sodium ion plus 1 electron, and you need 496 kilojoule per mole of energy for this ionization to happen. Okay, now sodium is ready to react with its counterpart. Okay, now comes chlorine. So what happens is first I have to convert the chlorine molecule into its atoms. So I need energy of atomization. So I convert chlorine molecule into chlorine atom, and I give it 242 kilojoule per mole energy to do this process. Then chlorine from chlorine atom accepts 1 electron to become chloride ion, and to this we call electron affinity. Here it evolves heat of electron affinity, that is the evolved heat is negative. So 348 kilojoule per mole energy it evolves. But last but not the least step of this reaction is combination of these both ions. The last step in these reactions is lattice energy. What is lattice energy? When the chloride ion formed over here, gaseous ion, combines with the sodium gaseous ion formed over here and form crystal of NaCl. So as discussed earlier, lattice energy is defined as it is the amount of energy evolved when 1 mole of an ionic crystal is formed from its constituent ions. 1 mole of an ionic crystal is formed from its constituent ions. So this is the definition of lattice energy. But we cannot calculate the lattice energy in this case directly because this is the fastest step of this whole process. So it happens very fast. We cannot calculate lattice energy directly through direct calorimetry. What we do is indirect calorimetry and use His law in Born-Haber cycle to find its lattice energy. Delta H1 is equal to delta H2. Delta H1 is 411, which is heat of formation of NaCl. Delta HF, formation of NaCl. And what is delta H2? It is delta H of sublimation plus delta H of ionization plus delta H of atomization plus delta H of electron affinity plus delta H of lattice energy. Okay, if this side equals this side, what can I do is, it is pretty easy. I have to put the values of these: sublimation, ionization, atomization, electron affinity, and I can find lattice energy. So I will add up all these energies and just bring them to the other side of the equation, and I can find that delta H of lattice energy is equal to 789 kilojoules per mole. So this was the whole discussion about lattice energy in Born-Haber cycle. Why I discussed it, first of all, to define to you what is lattice energy. Second, I hope the question is visible and clear. The question is saying the energy change in a closed cycle from initial to final state is 0. The statement obeys. Okay. So what is the statement saying? That you start from a point 1, go to some point, and then reach to point 1 again. So this is a closed cycle. Okay, anywhere around you came by any path, so it does not matter. So but you came to your first point again. So the energy change in a closed cycle means the energy remains conserved. Okay, so which statement does this obey? Born-Haber cycle, law of conservation of energy, first law of thermodynamics. So which statement does this obey? Is this obeying Born-Haber cycle? As we said in Born-Haber cycle, that the energy remains conserved, like delta H for path 1 is equal to delta H for 2, means if you start from the same point and you end up on the same point, you will have the same delta H value. So what is it obeying? It is obeying Born-Haber cycle. Yes, it is obeying Born-Haber. Law of conservation of energy. Yes, it is obeying the law of conservation of energy, because energy has not been destroyed during this whole process. Okay, is it obeying first law of thermodynamics? Yes, first law of thermodynamics is the law of conservation of energy. So it is obeying. The last topic for our today's discussion is heat capacity. We'll define heat capacity, then we will define different types of heat capacity, like specific heat capacity and molar heat capacity and their mathematical forms. I will derive a formula, and then on that formula, on the basis of that formula, we will solve a previous paper MCQ, and that will be the end of today's lecture. So first of all, what is heat capacity? It is the amount of heat required to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. So this is the amount of heat that is required to raise the temperature of an object by 1 degree of Celsius or Kelvin scale. So now we have written also the definition of the heat capacity is the heat required to raise the temperature by 1 degree C or 1 Kelvin. This heat is directly proportional to the temperature difference you want to achieve. So greater the temperature difference you want to achieve, the more heat you need to give to the system, the more heat you need to give to the substance. So this heat is directly proportional to the temperature you want to change. Okay, so to remove the proportionality sign, I put a constant here, in this case I C, to which I called heat capacity. Okay, now if I want to find the value of C mathematically, I can bring this temperature to a denominator. I will get heat over temperature difference is equal to C. C is heat capacity. So we can also derive its unit from over here, which is Q. We represent them in joules, so joule, and temperature in Kelvin or Celsius. So it could be joule per Kelvin or joule per degree C. Okay, now one more thing. This heat capacity depends upon the amount of substance, means this is an extensive property. Greater the amount of substance, greater will be its heat capacity. Like if I take an example, 1 kilogram of water requires 4,200 joules per Kelvin energy. Okay, but 100 grams of water requires 420 joules per Kelvin of energy. So means greater the amount of substance requires more amount of heat to raise its temperature by the same degrees, like here 1 degree. For 1 degree rise in temperature of 1 kilogram of water requires 4,200 joules of energy. But if you have 100 grams of water, you require 420 joules of energy to raise its temperature by 1 Kelvin. Okay, now what is specific heat capacity and what is molar heat capacity? So I will write them down over here. Specific heat capacity and molar specific heat capacity is the amount of heat required to raise the temperature of an object, but the object should be 1 gram. So this is the heat capacity for 1 gram of object. Other things are the same, but the mass of the object, the amount of substance should be 1 gram. So the amount of heat required to raise the temperature of a 1 gram object by 1 degree C or 1 Kelvin. Okay, mathematical form remains the same, that it is but here it is represented by S and could be written as it is the amount of heat required to raise the temperature of an object having 1 gram of mass by 1 Kelvin. Okay, so here S is specific heat capacity Q is the amount of heat required, M is the mass of the object, and delta T is temperature difference. Specific heat capacity, Q is the heat, M mass of the object, and T is temperature. This is not an extensive property. This is an intensive property, independent of the amount of substance. So specific heat capacity is independent of the amount of substance. It just depends upon the nature of the object. Now, what is molar heat capacity? Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree of Celsius or 1 Kelvin. So for this, the amount of substance must be 1 mole. 1 mole of a substance. It is represented by C. C is equal to a heat required to raise the temperature by 1 degree of 1 mole. The amount of heat required to raise the temperature of a substance by 1 degree, but that object should be 1 mole. There are different types of molar heat capacity. One is molar heat capacity at constant pressure, that is Cp, and one is molar heat capacity at constant volume, that is Cv. So I will write them over here. Cp, molar heat capacity at constant pressure, and Cv is the molar heat capacity at constant volume. So at constant pressure, I say Cp is equal to, I must take the Q at constant pressure, means Qp means the heat required to raise the temperature of an object, but this heat required must be at constant pressure. So Cp n remains the same and delta T remains the same. Here we know that Qp is equal to delta H, as we know that heat at a constant pressure is equal to change in enthalpy of a substance. So from here I can find I can put delta H in place of Qp, so delta H over N delta T. Now if I want to find delta H in terms of Cp, I can find it. Delta H would be equal to, if I bring this to the other side of the equation, delta H would be equal to Cp n delta T. Okay, now we know that Cv is molar heat capacity at constant volume, so Q would become Qv divided by N delta T. As we know from first law of thermodynamics, which says that Q is equal to delta E plus P delta V. When delta V at constant volume, delta V is equal to 0. At constant volume, delta V is equal to 0. So this term becomes 0, because 0 multiplied with anything becomes 0. So Q at constant volume becomes delta E. So I can put the value Qv, I can replace Qv with delta E. So here I'll put Cv equals delta E divided by N delta T. So now if I want to find the value of delta E, that is internal energy, I can find it. I can bring this to the other side of the equation, and delta E would become equal to Cv N delta T. So this is another equation for us. Now with the help of these equations, we can find enthalpy of a system and internal energy of a system in terms of molar heat capacities. So this was all about it, but we must remember this formula because we will solve in MCQs with the help of it. So the question was that the amount of heat required to raise the temperature of 10 moles of water. Number of moles is 10, n is equal to 10. 10 moles of water from 70 to 80 Kelvin. So the temperature has been raised from 70 to 80 means 10 degrees. So 10 Kelvin. Delta T is equal to 10 Kelvin. Okay. Molar heat capacity of water is, so molar heat capacity is given. We are required the amount of heat. Okay. We are asked to find the heat required. Okay, so we know the formula, the answers, the options are, we will find our answer and match with these options if any one of our answers relates to it or not. Okay, so we know by formula, by definition, the molar heat capacity is equal to heat required to raise the temperature on of an object of 1 mole by 1 degree. Okay, now we are given the molar heat capacity of water, we are given the number of moles, and we are given the temperature difference. So it is very easy. We can shift the denominator of the equation to the other side of the equation and find Q with the help of that. So Q would become C in delta T. So molar heat capacity is given, which is 75.24 joules per mole per Kelvin. Okay, and number of moles are given, which is 10, and delta T is equal to 10. So we can find it. 10 multiplied 10 equals 100. 100 multiplied 75.24, it will bring the 0.2 digits to our right, and our answer would become 75.24 joules. So this is the amount of heat required. One more thing I want to mention is the units. The units of specific heat capacity and molar heat capacity. Okay, so specific heat capacity, we represented it with S, Q, M, delta T. So put the units. Q is joule, M is in denominator mass of the object, so we can say gram, so per gram, and temperature in Kelvin per Kelvin, or in degree Celsius, so I can say joule per gram per degree C. Okay, in case of molar heat capacity, I could write C equals Q N delta T. So Q is in joules, number of moles unit is per mole, and temperature in Kelvin, per Kelvin or per degree C. So these are the units of specific heat capacity or molar heat capacity.